what we're going to do is a more in-depth presentation of a case study that we worked on together. We touched on it very briefly at a NASA Technique Briefs webinar called Model-Driven Innovation, the Role of Multi-Domain Dynamic Systems for Functional Verification in Model-Based Systems Engineering, or MBSE. You can find that recorded webinar available at techbriefs.com. So just to recap, what we were talking about is that really the role of our tools within the systems design and development process, typically presented as a V, and how in order to manage the relationship between system requirements and the actual system behavior, typically engineers will develop a functional mock-up based on the system structure, design structure, and the requirements. The functional mock-up is then used to do testing against those requirements in order to make sure that the design fully complies all the way through the process. So as you add more detail from detailed analyses, that information is added into the mock-up all the way through to make sure that the design is going to be robust. If you focus a little more on that side of the design and development process, there are tools that are available to manage those different steps. So, for example, Rhapsody, Magic Draw for SysML type of requirements modeling, through to system-level synthesis, through tools like ours, MapleSim, and from the MathWorks and other suppliers. And then, as you want to add more detailed analyses to the process, there are tools for doing finite element analysis and so forth, and all that information can be combined into the functional mock-up. However, that's quite a complex process when you want to try and bring all that information together in order to do the compliance testing, and that's where tools like ModelCenter from Phoenix can be used to bring all the various models and the results from various analyses together in order to do the requirements testing, and that's really the focus of this particular case study. The example we worked on is for an electric vehicle, where we're focusing on the battery system, and particularly the capacity, range, and also the thermal performance. So these are just a short list of the kinds of factors that we were considering when doing this, working on this example. First of all, when designing the system, we need to determine what the requirements are. So in terms of safety, performance, what the battery is going to do, how big it's going to be, what kind of charge density do we need, and also what the cooling system is going to require in order to maintain the temperature within the vehicle, within the driving system, and in particular in the battery system. So to do this, we've used Rhapsody as the tool for putting the requirements together as a requirements model based on SysML. That information can be then integrated into the ModelCenter environment, and then we can use Maple and MapleSim to Maple as an interface between ModelCenter and MapleSim in order to extract the model parameters, feed those into the MapleSim model, run a simulation, and then extract the salient information out of that simulation in order to feed it back into the ModelCenter environment in order to perform the compliance testing through the Phoenix's system engineering and integration module. Any changes that are required, or if there are any aspects of the design that are outside of requirements or to fail the compliance test, adjustments will need to be made to the design, and those changes can be fed back into the Rhapsody environment in order to do impact analysis and so forth. So that's just to give you a high-level description of what's going on in this particular demonstration. I'm now going to pass it over to Andy, who's going to take you through the requirements development side of things.
In a project like this, usually one would start out with determining requirements, and requirements, at least high-level requirements, are handed over by the stakeholders of a particular project, and so we would document those requirements in the model-based systems engineering context in a tool such as Rhapsody, which is what I'm showing to you right now. So what I'm showing right now is a requirements diagram. Basically, it's a way of describing what those requirements are, and then how those requirements are decomposed into much finer, much detailed requirements. So in this case, we have two example requirements. The first one is performance, and the other one is system limitation. So these are usually high level. They don't have specific quantitative values added to them. So they need to be broken down into smaller requirements. So for example, the performance gets broken down into the driving range, velocity, and acceleration. And these requirements then can be broken down some more depending on how high level or how much detail you want to put. In this case, what we've done is we've broken down the driving range, and we've added a quantitative value. So in this case, the driving range must be longer than 300 kilometers. So that 300 kilometers is a quantitative value that then we can use to compare with and calculate and compare and do some verification on. We specify in this case, we specify a lower bound of 300 kilometers as a property such that we can refer to. Now that we have requirements, we need to describe. And so we do that in a structural, in what we call a BDD, a block definition diagram. And what the BDD does is basically describes the environment and the actual system itself and how that gets decomposed and how different pieces of that system connects with each other. In this case, we have an example here of the vehicle. So a vehicle would be the electric vehicle that might have certain properties associated with it. In this case, it could be range, it could be weight that gets added, and that number is basically a property of that vehicle. Now, a vehicle is comprised of certain other pieces that can be broken down. So you break it down into things like a battery module, the body, the inverter, the motor. And then from there, you can also keep describing it down and keep drilling down into the different components depending on what you're looking at or what you're interested in. In this case, we have a second level on the chassis, with the chassis then has tires, for example. So, and each of these pieces or these blocks are described by certain value properties that we can use for analysis and also for verification with the requirement. Now that we have the vehicle and we have the requirements, how do those two relate? How do we relate them? And so we do that through what we call a satisfy relationship, and I have an example here of the satisfy relationship where we have the requirement of the driving range and say the vehicle weight, and we have the value properties from the vehicle. So we have a range and weight. So what we're saying is this range from the vehicle satisfies the requirement that has been created in the requirements diagram. So now, if the range changes, we can compare this range with this lower bound to see whether it satisfies or not. In this case, it does not satisfy because our current range for the vehicle is at about 170 kilometers, but our requirement says it needs to be greater than 300 kilometers. So this is the mechanism in which we connect the two, the value property and the requirements. Now that we've connected it, how do we know what the range is? So that is done through another piece called the parametric diagram. So what the parametric diagram relates those value properties and connects them to something called constraint blocks. These constraint blocks are basically calculations, or it refers to analysis that can be run and then update those value properties that were from the structure. So I'm going to zoom in on a section here just to kind of give you an example. So let's zoom in. In this case, we have a constraint block called component sizing. And component sizing then refers to analysis behind the curtain, per se, that we'll talk about later, that Joydeep will give you an overview. But these value properties then gets connected into an analysis that then can be run. And analysis can also, the output from an analysis can go into an input from another analysis or constraint block, and then you can create these parametric diagrams, creating workflows or relating these value properties to these constraint blocks. And then you can run them and then update those value properties, and then that gets compared with the requirements. So that's an overview of just how the systems model is created. Before we actually show this in action or show the analysis and how that flow occurs in action, I'm going to hand this over to Joydeep so that he can open up the curtain and actually show what goes on in Maple and MapleSim and ModelCenter in terms of what analysis is being made. So, Joydeep, over to you.
Thank you, Andy. Hello. MapleSim is a powerful tool that can be used to perform simulation studies for dynamic models of multi-domain systems. As we can see here on my screen, we have a dynamic model of an electric vehicle powertrain. It includes an electric vehicle model which has a vehicle dynamics subsystem. This vehicle dynamic model includes longitudinal motion dynamics, tire dynamics, fixed reduction gear from the motor, effects of aerodynamic drag forces, effects of tire sizing, and the effects of variable road grade conditions. The vehicle is being driven by a motor, which is modeled by a DC motor model that captures a particular torque speed characteristic curve, and also a motor efficiency map. The motor is powered by a lithium-ion battery pack, as shown here, through some power circuitry as captured in this particular block. The lithium-ion battery model includes a graphite lithium cobalt oxide electrode combination. It also captures thermal effects on the battery chemistry, temperature-dependent internal resistance, degradation effects of the battery, and also power electronics/inverter efficiencies. To keep the temperature of the battery under control, this model also includes a sub-model of a thermal system that is effectively a cooling system that actively and passively extracts heat from the battery. It implements a temperature control using a simple on-off thermostat, and it rejects heat through convection and conduction. The vehicle is being driven by a driver model which is tuned to follow predefined speed profile, and various properties of these models can be set manually by using MapleSim's property pane. To run the simulation, all that is required is to press this button, which generates what is known as the analysis window with all the necessary plots. In this particular example, we see 4 plots shown here. The target speed and the altitude of the road is shown on the first plot. The second plot shows the variation of battery temperature and the status of the cooling system. As we can see that when the temperature hits 30 degrees centigrade, the cooling system turns on, and when it reaches the 29 degrees centigrade, it shuts off. They also show the drive shaft torque variation and the variation of the state of charge of the battery throughout the duration of the simulation. Similarly, various other studies can be performed in MapleSim, and the effects of parameters can be found out by varying their values in the user interface, as shown here. Apart from MapleSim, it is also possible to perform detailed mathematical analysis on these models using what is known as Maple. Maple is a mathematical processing engine that can access any MapleSim model and perform mathematical studies. For example, if we load the exact same model shown here, we can see that the resulting temperature variation is shown in this plot. To see the effects of various parameter values, all that is needed is to change the value of the parameter and to click the update parameters. As we can see here, Maple automatically calculates the system response and updates the plots accordingly. Apart from simulations on MapleSim models, Maple can also be used for various data post-processing. For example, if somebody wants to calculate the performance of the thermal system, it can be performed using this worksheet by clicking here. As we can see here, the built-in code automatically calculates the average temperature, peak temperature, and the fraction of time the cooling system stays active for this particular simulation. Similarly, this section shows a very important calculation of the projected range of the vehicle. Using similar techniques, a host of other parametric studies can be performed on these models, which are important for systems-level verification and validation. Now, Andy will show you how these methods can be used for systems-level validation tests.
Thank you, Joydeep. So what Joydeep just showed you is basically the magic of analysis that happens behind these constraint blocks that then get, we can update, we can run it, and then update the value properties in the system and then compare that with the requirements. So let me just open up the integration toolkit, and it's a view called MBSE Analyzer. And MBSE Analyzer is part of a systems engineering integration module. And what it does is it connects everything. So it connects what Joydeep just showed you with what I showed you previously into one seamless evaluation. So I've opened up MBSE Analyzer, and I'm going to click on the Evaluate Designs button here. And the Evaluate Designs button lets you go ahead and go into the model and select the block, the containing block that contains the parametric diagram or owns the parametric diagram. In this case, I've just opened up the parametric diagram that I showed you here. And as you can see over here, all the value properties that's in that parametric diagram is listed with its units and its original values. So I can go ahead and change, say, one of this number. So I'm going to change this to 195 and run the analysis. When I click Run, what happens is it goes ahead and opens up ModelCenter that connects to Maple and MapleSim and runs the analysis that Joydeep just showed you just now, and then it brings the values back and the results back. And as we can see, we just got the results back, and we see the range and the weight just went up from its original value, and it compares it with the requirements. So if you see the margin here, we see that the range actually did not meet the range requirement by 126 kilometers. But it still does meet the weight requirement, and that's done through that satisfy relationship that I talked about earlier. So let's change it again to another number. Let's just go up to 200 cells and run and see what happens. So again, it goes back, pulls up ModelCenter, runs Maple and MapleSim, and then once the results are calculated, brings it back into this. So again, the weight margin has gone down, but still we meet, but we still haven't met the range requirement. The weight margin, but we have not met the range requirement. So one can go ahead and change these value properties to see what happens to the system itself and how that relates to the requirements. Once the engineer or the decision maker has found the correct design, they can either save it directly back into the model or save it as an instance or design instance into the model for to be recorded. Now, manually changing these values might be tedious, so we also offer a DOE or a design of experiments tool that will run the design of experiments around some of these values, or a parametric study tool. So to run the parametric study tool, you basically move something like let's just look at the number of cells right now. So that's the number of cells, and let's run it from say 180 to 220 at a step size of 5. And we'd like to say look at range. So I'm going to pull range in here and weight in here. Now, once we're done, I can hit the run button and it'll go ahead and run that analysis. Now that's going to take a while, so I have already run one that a priori so that you can see. So once it's run, all the results that you put in is over here. So in this case, I just changed the number of cells from 180 to 225 and looked at what happened to the weight and range. Obviously, you can add more variables to look at if I wanted to, and we also do plot how the run number and the weight. So let's just change that to the number of cells and see how that works. So this is how the weight changes with the number of cells, say, for example. So those are the tools that's available to you in MBSE Analyzer or the Systems Integration Tool module that connects the systems engineering world with the analysis world. So I'm just going to close this. So I'm going to hand this back to Paul just to kind of wrap this up.
Okay, thanks a lot, Andy, and Joydeep for that detailed dive into this particular case study. Just to summarize what we've been talking to in this presentation, MBSE, or Model-Based Systems Engineering, is shown to be a proven business process for managing design complexity, risks, and costs, and there are many tools that are available for supporting that process. Maple is a powerful environment for data pre- and post-processing, as well as managing executable requirements. It also provides the interface into MapleSim for rapid functional verification of complex multi-domain dynamic systems. And it's all brought together by ModelCenter for rapid requirements compliance testing, trade-off studies, and impact analysis due to changes in the design requirements. So fundamentally, by bringing all these tools together, this conversion provides a consistent and robust workflow for doing model-based systems development using our tools. With that, I'd like to thank you for your time and attention. If you'd like more information about what we've shown in this presentation, you can find the COSI website that talks about the MBSE standards and technologies. Phoenix Integration, for more information about ModelCenter and the Systems Engineering Integration module, and Maplesoft for more information about Maple and MapleSim.